Hello guys, this is CodeNCode and this is a video lecture for the introduction of Centroid decomposition. So in this lecture we are going to see the introduction of Centroid decomposition, and we are also going to see some of the problems you can solve using Centroid decomposition technique. So what is the intention of making this lecture is that I'll be giving you a very little introduction to centroid decomposition, and then there are some problems that should be in your mind when you see that introduction, and there are 4 or 5 questions that should be in your mind, and I'm going to give you those so that you can live with those questions for like 1 or 2 days until some hours, I guess, at least 1 day, so that when the next lecture comes you get all of your questions or queries get answered. So let's start the lecture. So why do we even need centroid decomposition? So first of all, you should know that centroid decomposition is a technique which works only on trees. It does not work on graph. So why do we even need centroid decomposition? So see, suppose there are queries and you have to find the ID. These are the IDs of the node 1, node 2. These are the IDs. So suppose you are given certain node X, say 8, and you have to find the nearest node colored red. So assume all of the some of the nodes are colored white and some of the nodes are colored red. Here none of the nodes have been shown colored red, but suppose this node and this node and this node 3, 5 and 11 are colored red, and this node 8 is given in the query, and you have to find the nearest node, the ID of the nearest node from node 8 which is colored red. So you can see 3, 11 and 5 are colored red. I mean, these are not actually colored. I'm telling you that these are the nodes which are, assume that these are the nodes which are colored red. So how you are going to solve this problem? How you are going to find the length, I mean the node which is nearest to 8 and is also colored red? Well, you can solve this problem using DFS, but the problem is it is going to take because of n time, assuming there are n nodes, because DFS runs in because of n time for tree with n nodes. Now the same problem can be answered, the same question can be answered using centroid decomposition in log n time. So you can see how the time complexity is being improvised from pico of n to directly log n. And what is the purpose, I mean how this happens, what is the structure of query answering, what technique we use, all of this we will be answering in this series, because of course we are going to see how we implement this. We will also be studying the implementation. We will also be solving 2 or 3 problems to make things crystal clear. Now let me show you 1 or 2 problems that you can solve using centroid decomposition. First, and one of the easiest I believe, is seal the commander. Seal the commander is a problem in which you are given a tree. You are having n cities with n-1 connection between them, undirected roads, and you can reach any, there always exists a path between any 2 cities. That means this forms a tree. If there exist n nodes, n-1 edges, and there always exists a path, basically they are connected, that means this is a tree. So you are given a tree and each city has been assigned an officer, and there are ranks. Ranks are denoted with A to Z. A is the highest rank, Z is the lowest rank. So the question says you are given a tree, and there is a special rule. There are enough officers for each rank, but there is a special rule must be obeyed. If X and Y are 2 distinct cities and their officers have the same rank, so if there are 2 cities but their officers have the same rank, then on the simple path between X to Y there must be another city Z, and the officer in that city should have the higher rank than these 2, and you have to tell whether it is possible or not, assignment of rank such that this condition follows. I mean, you can if the problem statement is not clear, you can of course Google the problem, seal the commander, and try to read the problem yourself. And one more thing, try to also read the editorial for the problem so that you can understand what approach we are going to solve this problem. If I show you the code for this problem only, I mean just to show you that how centroid decomposition looks like. See, DFS0, DFS1 and DFS. There are 3 DFSs used for this problem. I mean, when you are working with centroid decomposition, you need at least 2 DFS. And in the beginning you can think, okay, there are, I mean, it is a very big code. I mean, there will be at least 100 lines of or 150 lines, but this is the most easiest problem you can solve. That is why this is, I'm showing you the first. So this is the easiest problem you can solve. Then comes this problem, Xenia entry, and this is a little bit difficult. Then seal the commander, and it is rated 24, not just because it is rated 24, but because the implementation is a bit difficult and we have to think more to solve this problem. In fact, this problem is the same as we are discussing here, almost the same. Here there are 2 types of query, and first query is the initially there are n nodes. Of course, we are talking about the tree. Initially we are having n nodes. Each node is being colored blue, I guess, to be painted blue. Initially, consider the node initially painted red. All of the nodes are initially painted red and they are to be painted blue. Initially they are painted red. So there are 2 types of query. Query 1 says paint the specific node red, and initially they are red, paint a specified blue node to be red, which means initially they are blue. We will also consider the first node to be initially okay. Only the first node is initially painted red, the rest are painted in blue. So the rest are painted blue, and only the initial node, the root node, is painted red. So the queries are paint the specified blue node into red one, and then of course you are given a specific node and you have to find the closest red node and shortest distance. We have to print the shortest distance to the closest red node to the given specified node. So this is exactly the same question that we are discussing here, but here in this problem there are updates as well. So you can see the number of nodes are times power 5. In query can be also times power 5. So of course you cannot even imagine solving this problem using simple naive approach using DFS only. So just let me remove it. So see here, this is the easiest problem you can solve using centroid decomposition. Then comes this one. I'm telling you the specific order in which you should solve the problem, and then comes this problem here. The problem till now we have seen are this problem is different than the first 2 problems in a sense that, let me just show you here. The tree that we are talking about are unweighted. That means the edges that we see, the edges do not contain any weight to it. So what we can do, we can consider each edge to have 1 unit of weight. That is, we can assume, because none of the edges are having weights. But here in this problem the tree is actually weighted. So the problem here is you are given a undirected tree and each edge is having certain weight. So there are Q queries. Queries can be of 2 types. First, UVW, that means the edge between node U and V, we have to assign weight W. We have to basically update the weight, initial weight whatever was, we have to change it to W. The second query says you are given a node V. Just let me increase the font. So the second query says that you are given a node V and you have to print the length of the longest simple path passing through V. So basically if I've given you node 1, so there are many paths that go through 1. For example, 412 is a path that goes through 1. 7412 also a path that goes through 1. 4125 also goes through 1. So how many paths are there which pass through 1? In this case it is easy, because one of these, choose one of these endpoints and then choose one of these endpoints, so you can calculate using combinatorics how many paths are there. When there is a given node and you have to you have been asked to find the length of the longest path passing through that node, there can be a lot of paths passing through that, and even using naive approach you won't be able to pass one or two test case for this problem. So of course we have to go for some approach which is different than naive, and of course in this case we will be using again centroid decomposition. And this problem is different than the first two that I've told you, in the sense that in this case we are having weighted edges, while in the first two problems, in fact in the most of the problems using centroid decomposition, you will see that the edges are actually unweighted. Now in the fourth problem, this is one of the favorite problem that I've solved. I do not know which ID I used to solve this problem, and because I'm not getting the checked sign here, because I remember I have solved this problem because it took me like 2 days to solve this problem. This is one of the hard problem on CodeChef. Prime distance. The only best thing that I find about this problem is this: the problem statement is only of 2 lines. So let me increase the font again. 140 should be good. So you are given a tree, and this problem is actually a probability based problem, so it requires having knowledge of number theory, because we are talking about primes, and also of course the problem will be solved using centroid decomposition. We will be solving the problem using centroid decomposition. The other guys also have solved this problem using FFT. We haven't studied FFT yet, so of course we won't be solving this problem using FFT. So you are given a tree, and what you can do, you can select at random 2 distinct node, and then of course you would choose them uniformly and randomly. Of course we are talking about when you see these two words, randomly and uniformly, of course something goes through your mind, and that is probability, and you are damn right. So if you select 2 nodes uniformly and randomly, what is the probability that the distance between these 2 nodes is a prime number? This is the problem, and this is, of course, you can't even imagine solving it using DFS, because of course if there are n nodes, there are n into n minus 1 divided by 2, roughly n square number of nodes. And if there are pairs, if there are n square pairs, roughly overall algorithm becomes n cube, because each time you choose a pair and then you find the path between them, the length of the path between them, and that you can calculate using of course it would be n square log n in the best manner if you are using naive approach with binary lifting to calculate the distance between 2 nodes. Distance between 2 nodes can be calculated using binary lifting in log n time. So of course this is the third problem, and this is the most difficult out of all of these 4 that I've shown you. This is the easiest one. This is a bit more difficult. This is a bit on the same level as this, but just a slight difficult than the previous 2, and this one is the hardest. Of course this is a hard problem, and believe me, out of all of these 4, this is the hardest problem that we'll be solving. If I explain you the how much time I need to explain this problem to you, it took me like more than 24 hours completely thinking about this problem. What I'm making mistake, I had made a lot of submission for this problem and have spent a lot of time solving this problem. I solved this problem 1 or 2 years ago, and when I was learning centroid decomposition, and this problem really gave me hard time. Now if I explain you how much time I need to explain this problem, I think I need at least 3 lectures to explain you this problem, each lecture being half-hour long. I mean that's how much time I need to explain this problem to you, maybe, but at least 2 lectures half-hour long. And this is the 5th problem, black and white. The problem you can Gerald 2, you can Google and learn it yourself. This is till now I haven't solved this problem, so this is only to tell you that okay, this problem also you can solve, and there is also this problem BTS maintenance. Of course this is an advanced difficulty level advanced, and maximum score 140. This is also a problem you can try to solve once you have learned. So these are the 4 problems that we will be discussing. These 2 are left as an exercise for you. I have no idea what is the difficulty level of these 2 problems because I haven't solved them. These are just for a suggestion for you to solve this problem yourself. This problem, you are gonna love this problem, believe me. Of course, if there is some problem which can be solved using FFT, for those guys who do not know what is FFT, FFT is a fast Fourier transform you use to multiply 2 polynomial of degree n in n log n time. Usually it requires n square time, but FFT converts it, reduces the time complexity to n log n. Now that we know that what kind of problem can be solved using centroid decomposition, and we know for that how much time it saves us, let's go for some of the problems that I've told you. First of all, this is the tree, right? And this is centroid decomposition of that tree. Now see, when you see this centroid decomposition, the new tree structure, which is of course the centroid decomposition of this old tree, there are similarities you can see between these 2. First, both are tree. Second, both have the same number of nodes, and I do not know about third. So let's go for the problem. The questions. The first question that should come inside your mind is, why do we need an extra structure, a new structure? Because when we are going to answer the query, most of the time we'll be working on this. We do not need this. Once we have developed this structure, what we will be taking before answering any query, we would require to have a pre-processing, and after pre-processing we will be converting this tree into this structure, this new tree, and we'll be working on this, not on this. This is called the centroid decomposition of the original tree. Now the question is, why do we need an new structure? Why can't we use the original one? So the answer of this, you would be understanding the question is the most important, I believe, because this would tell you this would explain you what is exactly centroid decomposition, and in the next lecture I'll be explaining you why we need this structure, and why this, and how does this new structure helps you reduce the time complexity to log n. I'll be taking an example, a very beautiful example, so that most of the things are crystal clear to you, and you would know exactly why we need this structure and exactly how this structure solves the problem, reduces the time complexity. So this is the first problem. I want you to think over and over and Google and do whatever you can do your own research to find out why do we need a new structure to solve the problem in centroid decomposition. The second question is, why there are some edges in new structure which are not in the original tree. So you see, there must be some edges which are not in the original tree but are there in the centroid decomposition. For example, 411, yeah, there's no direct edge between node 4 and node 11, but here you can see in the centroid decomposition tree there is a connection or edge between 4 and 11 nodes. So when you see these, so of course when you ask this question, first, why there are new edges which are not present in the original tree, this is one question. But when this question arises, of course you know these edges have different meaning than these edges. Of course they have to have different meaning. If they both have same meaning, these edges show that okay, these 2 nodes are connected. But here, of course, that is not the meaning of the edges, because if that is true, then 4 and 11 must have been connected, but they are not connected. So what is the meaning of these edges? First, why there are new edges? First question is, why there are new edges in the structure? And the second question, if there are new edges, that means they don't have the same meaning. In the original tree, it represents the connection between these 2 nodes. There is a direct connection between these 2 nodes, while in the centroid decomposition tree, this is not the meaning of the edges. So of course the next question becomes, what is the significance of edges in the new tree? What is the meaning, what is the significance of each edge in the new structure? This is the next question that should come in your mind when you are looking at this structure. And the final question, I guess, yep, the final question: what is the height of the new structure and why? As you can see, it always the height of the tree always depends upon the uh, root. So height of when there is a question, let me tell you, the height of the tree is the new structure is going to be log n, no more than log n. And the question is why. So again, the answer of this question I'll be telling you in the next lecture, when I'll be explaining you what is this structure. We'll be studying all about this structure, and this is the most important step towards studying centroid decomposition. I do not think any person who explains centroid decomposition goes through this step, because this is the most important step. I have read 1 or 2 articles which are really good, the rest are just rushing through the lecture, and that is not how you do this. I mean, that is not the way to do justice with this approach, this algorithm, this data structure, whatever you call it. I do not know whether this is an algorithm to answer queries, of course. So I think Tanuj Khattar is the name of the guy. I really respect that guy. I have studied 2 or 3 things from that person. If my internet is working, let me show you Centroid. Yeah, here you can see centroid decomposition. This is the article, you can go and read it yourself, written by Tanuj Khattar, and I hope I'm pronouncing his name correctly. This guy have explained centroid decomposition in a very beautiful manner. So if you want to study it from here, of course you are more than welcome. You can go and you can read from here. I myself have studied centroid decomposition from this article, and the Tanuj do not only explain this thing, but also let me show you, also discusses the problem that can be solved using centroid decomposition. So he discusses the problem Xenia entry, I guess, and also Q35. Yeah, Q35 is one of the problems that can be solved using centroid decomposition as well. And he has given some of the he has also discussed the prime distance on tree. And even if you are studying from here and you are trying to solve this problem yourself, this is going to take a lot of time, believe me. Never mind. This is also the problem you can solve using centroid decomposition. And this article, the link to this article, I'll be putting in the description of this video. So if you want to learn from here, which I highly encourage, even though I want to have more views on my video, but it doesn't matter. First thing that should be a priority is study. So if you want to learn centroid decomposition, if you want to read something about centroid decomposition, if you want to learn centroid decomposition by reading, of course I will highly advise you to read this article. This is, to be honest, this is the gem, GEM, because my pronunciation is not that good and I do not care about that as well. So if you want to study, of course I'll be putting the link of this article in the description. So this was all for this lecture. Till the next video drops, there are many things I'll be explaining about this structure, why the height is log n, how this helps, why do we even choose to create new structure, what is the purpose of putting 2 to the root, why these are on the leaves, and any other question that we had here and the question that we do not have here. So this was all for this lecture. Thank you guys for watching. Until the next video drops, keep coding. Thank you.